In 1972, French speleologist Michel Siffre descended into a cave in Texas. There he spent 6 months in complete isolation, without a watch, without even the faintest glimmer of sunlight. His mission was part of a NASA project to study how the human body reacts to prolonged periods outside of Earth's natural rhythm. He lived on a free schedule, eating when he wanted, sleeping when he felt tired, turning the cave lights on and off at his own discretion. People tend to cope very poorly with such experiments. Siffre suffered from bouts of depression, memory lapses, forgetfulness, and even contemplated leaving our mortal world. But the most interesting part was what happened to his perception of time. In the first few days, his subjective day stretched to 25 to 26 hours, which is unusual. However, this was just the beginning. Gradually, Siffre's subjective day, the period when he was awake, reached 32 hours, and his night when he slept reached 16. Thus, sometimes his day lasted a full 48 hours, which is twice the norm. On the 179th day, Siffre was informed that the experiment was over, and he was very surprised because he believed he had only been in the cave for 151 days. That is, his internal sense of time had slowed down so much compared to reality that he was off by 28 days. And that's strange. It would be one thing if he were having a pleasant time, but to underestimate the passing hours when you're going crazy alone in a cave. However, this form of subjective time dilation has been observed in numerous other similar cases of human isolation, sometimes in an even more pronounced form. In 1988, Véronique Leguin spent 111 days in a cave in France, and when she surfaced, she believed only 42 days had passed. In 1989, Italian interior designer Stefania Follini spent 4 months in a cave at great depth, but she herself thought she had been underground for only 2 months. In 1993, an Italian sociologist lived in an underground cave for an entire year, and upon emerging thinking it was summer, he learned it was already winter. These cases vividly demonstrate that our subjective perception of time is not objective. You might say, aphelion, like any subjective experience, subjective time is a product of brain activity and does not exist outside the human skull. Just as, for example, there is no color in nature. Color is merely the brain's interpretation of a narrow spectrum of electromagnetic waves. They have as much in common as the letters of the alphabet and the sounds we assign to them. And of course, like most subjective sensations, the sense of time is susceptible to illusions and distortions. Yes, but wait a minute. Indeed, when we look around, we see a coherent picture of the world created by the brain. However, when it comes to a subjective phenomenon, like color, we know, as much as one can know, that color has a physical equivalent. And that equivalent is the wavelength of electromagnetic radiation. That is, the brain, albeit subjectively, interprets something objective, a phenomenon that truly exists in nature. But what does the brain interpret when we speak of the feeling of time passing? What in reality is the equivalent of this sensation? If you think this is a stupid question with an obvious answer, then you don't even know the little that science has discovered about time to this day. Because what you are experiencing right now, the sensation of the present moment, is one of the major unresolved scientific mysteries. But let's not rush and leave aside our subjective experience for now. What is objective time anyway? This comes with significant problems as well. Even St. Augustine, a philosopher and theologian over 1,500 years ago, wrote, "What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know." And physicist Richard Feynman said, "It would be nice if we could get away from it. Time is one of the things we probably cannot define. What is really important is not how we define time, but how we measure it." So the working definition literally is, time is what a clock measures. But if we still try to answer this question in a somewhat detailed way, most people would intuitively conclude that time is a sequence of events flowing from the past to the future through the present. Moreover, only the present moment is real, because each instant receding into the past simply disappears, and the future is yet to happen and does not currently exist. And in general, the past and future are merely our abstractions. But modern physics unambiguously hints that, In reality, the true picture of the world is nothing like this description, and that, whatever time may be, our intuitive understanding of it is simply inadequate. Many don't even realize just how much. Let's consider one thought experiment that everyone has heard about in one form or another, so many times that we have simply stopped paying attention to it. And we certainly don't even try to ponder just how paradoxical the conclusions about the surrounding reality that can be drawn from it might be. I will describe it quickly. Imagine a strange train with a single carriage 400,000 kilometers long, moving in a straight line at a speed of 200,000 kilometers per second. Right in its middle stands a man. He has a pistol in each hand. One pistol is aimed at the window at the front of the carriage, the other at the window at its end. And these pistols are so powerful that the speed of the bullet fired from them is 200,000 kilometers per second. When the man in the carriage fires, exactly 1 second later, both windows will shatter, and this will happen simultaneously. It seems obvious. However, if at the moment of the shot, the man in the carriage was next to a man on a stationary platform, the man on the platform would see something different. The bullet sent backward would also shatter the window after 1 second. Relative to the train, its speed would be 200,000 kilometers per second, but relative to the platform, 0 kilometers per second. And this is absolutely legitimate. But the bullet fired forward, relative to the carriage, moves at 200,000 kilometers per second, but relative to the platform, already 400,000 kilometers per second. That is the speed it must have from the perspective of the man on the platform to reach the front window in 1 second. However, we know that 400,000 kilometers per second is an impossible speed. It is 100,000 kilometers per second higher than the speed of light. Therefore, the bullet's time will slow down due to the effects of special relativity. And according to calculations, from the perspective of the man on the platform, its speed will be only 277,000 kilometers per second instead of 400,000. The windows will not shatter simultaneously. The rear window will shatter first, and only later, with a delay, the front one. And it's not a trick of vision. No, it's an objective fact. The special theory of relativity has been tested in so many ways, and with such monstrous precision that we can say unequivocally, if the above experiment were conducted for real, this is exactly how it would happen. This phenomenon is called the relativity of simultaneity, and it tells us something absurd about the world we live in. It's as if we have two different realities. In one, both windows are either simultaneously intact or simultaneously broken. But in the other, there is a moment when the rear window is already broken, but the front one is not yet. These are not two different universes. Both people are in the same universe. Because if they talk to each other, they will disagree about when the windows broke. So whose reality is real? However strange it may seem, the special theory of relativity tells us that both realities are absolutely equal. If you've watched videos describing similar thought experiments, then I don't know why, but at this point, everyone usually just stops and goes no further. Saying like, yes, that's just how reality is. But how? How the hell should a universe where this is possible look? After all, contradictory statements cannot be simultaneously true. This violates the laws of logic. The model of the universe corresponding to the laws of physics contradicts intuition. It doesn't resemble how we feel time inside ourselves. And perhaps the reason is that the brain, this limited biological tool, was forced to adapt to a world where the very idea of sequence is a fiction. American neuroscientist Dean Buonamano dedicated years to studying how the brain encodes time. He gathered the results of work by physicists, philosophers, psychologists, and came to a conclusion. Perhaps the sensation of time is an illusion, not just a perceptual inaccuracy, but a consciously constructed lie, without which the brain could not exist. Einstein explained the theory of relativity through examples where time and space depend on the point of view. But Buonamano adds something else: dependence not only on speed, but also on the observer themselves, their biochemistry, neural networks, perceptual limitations. Time is not a flow passing through us. It is a scheme our brain builds to not go insane from the chaos of events. Inside the brain, clocks are working, not mechanical but neural, embedded in tissues, regulating the rhythm of sleep, wakefulness, memory. They synchronize billions of processes, determine when a cell should divide, when to release a hormone, when to feel hungry. But the brain is not just a timekeeper. It is a predictor. It lives not in the present, but in the future, a fraction of a second ahead. To survive, it needs to know what will happen next. If a rubber ball rolls off a table, we automatically move to catch it when it bounces off the floor, but we react completely differently if a piece of pie falls from the table. Humans, like other animals, constantly try to make predictions for various time periods. Bring a cat into a new house and observe how it tensely builds a mental map of the area, sniffs around, prepares for what might happen not only in a few seconds, but also in a few minutes or even hours. When a wolf stops to catch certain signs, sounds, and smells, it is looking for clues that will help detect potential enemies, prey, or a mate. When a dog jumps up to catch a frisbee, it must know where the plastic disc will be in a second. And this, again, requires the ability to predict. Pollinating birds can measure the time interval since their last visit to a specific flower, so that by the next time the flower has had time to refill with nectar. Literally all manifestations of life, from the ability to hit a moving target with a spear, understand when to laugh at the end of a joke, or play Beethoven's Moonlight Sonata, to the ability to regulate the daily sleep-wake cycle or the monthly menstrual cycle, all require the ability to determine time. The brain doesn't just count the seconds, hours, and days of our lives. It recognizes and creates temporal patterns, such as musical rhythms and precise sequences of movements that allow a gymnast to perform acrobatic tricks. Our natural desire to clap our hands, snap our fingers, or nod our heads to the beat of the music is further evidence that the human brain is constantly engaged in prediction. Music is one of the most precise examples. When the rhythm is disrupted, we feel anxiety. Our internal clocks are thrown off, and the brain is forced to rebuild its prediction to restore the illusion of a smooth flow. The brain hates unpredictability. The sound of dripping water in a cave drives one mad not because it's loud, but because it's irregular. When there is no pattern, the brain cannot relax. It is in constant readiness to catch the next event, to restore the order of time. But here's what's truly alarming. The brain itself creates the illusion of continuity. When we blink, the eye is closed for almost half a second, and during that time we see nothing. But the brain cuts out this moment, stitching the frames together like film clips. We live in an edit. Consciousness is a movie edited from fragments of perception where missing seconds simply do not exist. But the only thing we experience directly is the present moment. In reality, we cannot be in any moment other than now. And at the same time, when trying to catch this very now, it immediately slips away. But not for everyone. There is one person with a rare, specific brain injury because of which his present moment, about 40 years ago, in a sense, still stopped. We are talking about the British music critic Clive Wearing, who after a severe infectious disease and damage to the hippocampus, completely lost the ability to form new, stable, long-term memories. This is one of the most severe cases of amnesia in the world. His memory of events lasts from 7 to 30 seconds. His entire life consists of, on average, every 20 seconds, as if, in quotes, waking up, resetting his consciousness after his short-term memory expires. And every time for almost 40 years now, he feels as if he has just emerged from a coma. If a conversation lasts longer than a few sentences, he loses the context. He was advised to keep a personal diary, which he did. But if you look inside, we see, for me personally, a horrifying picture. Page after page, entries like 8:03 a.m. Now I am really fully awake. Then crossed out. 9:06 a.m. Now I am completely, absolutely awake for the first time. Ignore the last entry. Crossed out again. 9:34 a.m. Now I am supremely, truly awake. Studying his diaries, we see that at some point he starts writing the time in large numbers, and does so with such pressure, as if trying to anchor himself in the continuum, to catch the train of time. Is this not a little death, every few tens of seconds, that he is so desperately fighting? He writes again and again in huge letters, "I am alive." And each time he doesn't know who made the previous entries or when, although he recognizes his own handwriting. Since Waring cannot understand where he is or how he got there, the only possible interpretation for his brain is that he has just woken up. An endless loop of a single moment. And if you are tormented by the question of what this might feel like, then in a 2005 documentary, Clive answers such questions. "You are the first people I have seen. You three, two men and one lady, the first people I have seen since I became ill. There is no difference between day and night. No thoughts at all, no dreams. Day and night are the same, empty, just like death." Clive, tell me, is it very hard? No. It's exactly the same as being dead. It's not hard at all, is it? Being dead is easy. You don't do anything. You can't do anything. When you're dead, it's the same. Exactly. Do you miss your former life? Yes, but I never realized I was thinking about it. So I was never bored or sad. I have never been anything at all. It's just like death, not even any dreams. Day and night are the same. This is a tragic story. While it doesn't directly prove it, it still suggests that for humans, the moment we call now is linked to short-term memory. And it doesn't happen in an instant, but rather in jerks, having a certain duration in time. That is, the conscious sensation of the present can be more compared to a musical note than to a frozen film frame. Our brain constructs continuity not because it exists, but because we cannot exist without it. Scientists call this the window of integration. It usually lasts about 2 to 3 seconds. Everything that happens in these seconds, the brain glues together into a single experience. This is our present, but it is not instantaneous. It is already the past, digested and constructed. When you see lightning, it has already struck. When you hear music, it has already sounded. Consciousness lives with a delay. The world in which we supposedly live, here and now, is a simulation made of memories, slightly lagging behind physical reality. Physics also finds no place for now. Neither in Newton's equations, nor in the theory of relativity, nor even in quantum mechanics is there a variable meaning, the present moment. The universe does not move in time, it is. Mathematician Hermann Minkowski, Einstein's teacher, was the first to propose thinking of space and time as a single four-dimensional whole. Space-time. In this model, past, present, and future exist simultaneously, like different points in one giant crystal. We do not move through it. We simply exist in it, embedded in layers. This picture is called the block universe. Imagine a DVD. The movie is recorded in its entirety. All scenes from beginning to end are already there. We simply watch the frames in order. But there is no time on the disc. It is born only at the moment of playback. If the universe is a block, then the question, why does time move forward, loses its meaning. Everything already exists. Birth, death, memory, future are simply coordinates in a four-dimensional structure. We feel movement not because it is real, but because our consciousness passes through this structure, frame by frame. Philosopher Julian Barber wrote, "Change is an illusion. We see motion not because time flows, but because our perception jumps between static states of the universe." Thus, the brain creates a movie from static frames of reality. And in this film, it seems to us that something is happening. But there is something even stranger. If time is an illusion, why do we still feel it stretching and compressing? We can overestimate the amount of time we spend in queues or waiting for a phone response by as much as 2 times. That is, every minute lasts like 2. On the other hand, research shows that when listening to music, waiting time feels shorter. Companies use this, which is partly why you hear music when waiting for an operator. So people can, to a certain extent, slow down or even speed up their experience of time. But what scaling possibilities will we have if we talk about time not as something we perceive, but as a physical process? If we start dividing time into smaller and smaller intervals, will we ever stumble upon a, how to say it, fundamental unit of time that can no longer be divided into an even shorter unit? Hours, minutes, seconds, milliseconds. That's not it. Maybe a nanosecond or a femtosecond. The indivisible unit of time is called a chronon. And while clocks are the most precise instruments we have ever built, in a way, humanity has even become a bit obsessed with its desire to learn to determine time. Centuries ago, clocks were rarely synchronized with each other, but now, from Einstein's general theory of relativity, it follows that the time measured by any clock is subject to the influence of gravitational forces. Therefore, the same atomic clocks will tick faster on a space satellite than on Earth. But generally speaking, think about it. The readings of the two most modern atomic clocks will diverge if one is placed on the floor and the other on a table. Can you even imagine that? Once, Richard Feynman said that due to the effects of the theory of relativity, due to time dilation, the Earth's core should be noticeably younger than its crust. He assumed a difference of a few days, but recent calculations have shown that over the entire existence of the Earth, a difference of about 2.5 years has accumulated between the core and the crust. That is, from the perspective of us humans living in 2025, the core is still in 2023. Currently, we have learned to measure time more accurately than any other parameter, and many quantities are defined precisely through it. For example, the definition of a meter literally sounds like the distance that light travels in 1/299,792,458 of a second. The progress in measurements is simply insane. But despite this, science still has no answer to the question of whether time is discrete or continuous. Many experts agree that the existence of separate instants would lead to paradoxes, like Zeno's dichotomy paradox. The modern formulation of the paradox is, to cover a distance, you must first cover half the distance, and to cover half the distance, you must first cover half of that half, and so on to infinity. Therefore, movement never begins. Similarly, if we imagine that every action takes a certain number of instants to complete, and every instant takes time to end, we encounter an infinite chain of instants necessary to complete the action. This means the flow of time cannot even begin. This is part of the mystery of time, the essence of which we are slowly approaching. Here, in my opinion, begins the most unpleasant half of the video. Physicists believe that the division into past, present, and future is just a stubborn illusion. Albert Einstein. You've probably heard many times that the laws of physics are symmetric with respect to time, that they don't attach special significance to the direction of time, and that no special moment, past, present, or future, exists for them. Past, present, and future are equivalent to each other. Thus, now, on the time scale, is the same as here in the realm of space. For this reason, many physicists and philosophers believe that any moments on the time scale are equally real. However, this minor point is not the most serious argument for, say, Alexander the Great being as real and existing in the same sense as you and I. The main confusing concept is Einstein's theory of relativity. The train example from the beginning of the video demonstrates that each observer, depending on their speed and direction of movement, has their own independent concept of the present moment. Each has their own set of simultaneous events, which are not necessarily simultaneous for other observers. As I said, those who talk about this usually stop here. But here begins what simply blew my mind. The effects of relativity demonstrated by the train example sound cool, but they are extremely detached from our everyday reality. We don't encounter such crazy trains. So what does it matter to us? How can it even influence the picture of the world we perceive? To understand, let's go a little further. In his book, The Emperor's New Mind, concerning computers, minds, and the laws of physics, Nobel laureate in physics Roger Penrose presents a thought experiment that simply forces one to reconsider one's own ideas about reality. The point is that even at very small relative speeds, changes in chronology become not only noticeable, but colossal. If 2 points are at great distances from each other, for example, 2 people slowly passing each other on the street, they won't see a difference in the events happening around them. But if at the moment they pass each other, we teleport to the Andromeda Galaxy at a distance of 2.5 million light years, which on a cosmic scale is not that much. The events simultaneous, according to these two passersby, would be separated in time by several days. While for one passerby, a space fleet sent with the mission to destroy all life on Earth is already in flight. For the other passerby, the decision to send the fleet has not yet been made. If this happens, it has a dramatic impact on our understanding of time. Let me remind you, the special theory of relativity has been tested with unimaginably high precision. An important caveat is needed here. Neither passerby can actually see or know what is happening in the Andromeda galaxy. Light, like any information, will reach Earth only after 2.5 million years. The argument is not about that, but that if we could make instantaneous, three-dimensional snapshots of the universe for each of the two pedestrians, these snapshots, at the moment the pedestrians meet, would be almost indistinguishable, but would begin to differ more and more strongly as we move away from the meeting point. And another important clarification, it's not just about conscious observers. This situation applies to any material point. That is, it doesn't matter if it's people, stones flying past each other, moving particles, or anything else. All of it has its own frame of reference and its own set of simultaneous events. So as you can see, a paradox emerges. Two people who, from their conscious point of view, are in the same place at the same moment, suddenly have different sets of events in their so-called present moment. Again, these are not different universes where different events occur. If the second pedestrian, who is moving away from Andromeda, turns around and follows the first, his perspective on the events in space would become conditionally the same as the first pedestrian's. Conditionally, because full synchronization is impossible. I think you already see where the wind is blowing. If you look at the situation from the reverse side, it turns out that from the perspective of aliens from the Andromeda galaxy, the same thing would be happening in relation to us. For some of them, you exist in yesterday, and for others, in tomorrow. I'll ask the question again. How should a universe where this is possible look? The special theory of relativity tells us that there is an infinite number of planes of simultaneity passing through any given point in spacetime. And for each point in space, there are different, sometimes very different, sets of simultaneous events. Different planes of simultaneity. That is, even the slightest movement of your head changes the present moment you perceive. In the universe, everything becomes even more absurd when you realize that the spaces of present moments differ for your head, arms, legs, and body. Okay, I know I've already tired you out. So based on this data, what does the universe look like if we could fly beyond the boundaries of the cosmos and survey it with a glance? From the perspective of special relativity, we would see an unchanging four-dimensional block in which time exists as another spatial coordinate. We would understand that within such a model, the block universe model, to talk about now is the same as talking about here. Any present moment is real and exists on one of the sections of this block. Scientists, mathematicians, and philosophers, including Rudiger Rucker, note it is actually impossible to find any objective and universally acceptable definition of all of space taken at a given moment. This follows from Einstein's special theory of relativity. Thus, the idea of the block universe is more than an attractive metaphysical theory. It is a well-established scientific fact. Interestingly, when Einstein first published his paper on special relativity, he did not claim that time should be considered as the fourth dimension of a block universe. The first to make such amazing conclusions regarding the connection between space and time was his teacher from Zurich, Hermann Minkowski, who during Einstein's student days called him a lazy dog. It was Minkowski who cast Einstein's theory into a geometric form in 1908. Drawing on his earlier work, Minkowski announced with great solemnity, "The views of space and time which I wish to lay before you have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Of course, we cannot visualize or depict a four-dimensional block, but for a clear illustration, we can neglect one spatial dimension, as shown here. In such a representation, it will be even easier for us to understand what a plane of simultaneity is. For this, let's consider a more radical version. Take an Earthling and an alien creature from some galaxy, not 2.5 million light-years away like Andromeda, but 10 billion light-years away. If the alien and the human are at rest relative to each other, their clocks run synchronously, and the present moment for them lies on the same slice of the block universe. But if the alien starts moving away from Earth, the clocks will desynchronize. Let me remind you, for moving objects, time slows down. Thus, the alien's plane of simultaneity relative to Earth will be tilted towards the past. Let's say the aliens in the distant galaxy are not moving much faster than humans. The tilt angle will be small. However, at a distance of 10 billion light-years, even this small angle will give a huge difference in time. From the perspective of an extraterrestrial, the present moment on Earth would be some point in the 19th century. And this moment, according to special relativity, will be as real as the moment you're in now. By manipulating the alien's speed, direction of movement, and distance from Earth, one can make any moment in time the present, be it from the year 1000 or the 3rd century. This is one reason why faster-than-light travel in space seems very doubtful. It would lead not only to travel in space but also in time. One could easily fly to Andromeda and then return to one's own yesterday, which would cause paradoxes. But if you think that's all, no, this is only the beginning. Everything suggests that any form in space is formed by the intersection of a figure with a larger number of dimensions. A square is the result of a cube's cross-section. A circle is a cross-section of a sphere. Three-dimensional cubes and spheres arise from the cross-section of four-dimensional figures, about which people have hitherto only guessed and occasionally seen in dreams, wrote Howard Phillips Lovecraft. If you previously thought that time is like a river, the laws of physics say the river is frozen. Common sense suggests if we live in a block universe and events in the past and future are somehow fixed or even inevitable, then our internal feeling of free choice is a phantom. Any choice you are going to make in life has already been made. The side of predestination in life is not mandatory. Within the ideas of British physical technical research, different versions of the future are possible, but time still remains fixed. Against this background, it becomes interesting. Humans, apparently, develop the ability to understand the concept of time using the same mechanisms as for comprehending space. In other words, at a basic level, the brain may not distinguish between space and time. To move to the main mystery of the video and understand it better, we need to talk about this. The eminent Swiss psychologist Jean Piaget looked for parallels between psychology and physics. It sounds far-fetched, but wait. Piaget revolutionized developmental psychology by explaining the mechanisms by which children learn abstract concepts such as quantity, space, and time. Apparently, he believed in a deep connection between children's innate idea of the relativity of time and the relativity of time in Einstein's theory. To understand how time is reflected in children's minds, Piaget asked them to perform simple tasks. In one of them, he used two snakes that crawled along parallel trajectories for several seconds. For example, a blue one and a yellow one. Both snakes started moving from the same position at the same time and stopped simultaneously, but the blue one advanced further because it crawled faster. Children aged 5 to 6 mistakenly reported that the snake that crawled a greater distance stopped later. That is, the parallel with the theory of relativity is that children intuitively understand. For an object moving at a higher speed, time stretches. That is, we have an innate understanding of the concept of space-time. Of course, this is a strong statement. However, Einstein himself, mentioning Piaget's ideas, said that this theory is so simple that only a genius could have thought of it. Let's imagine how the brain works in adults. Two light bulbs light up in sequence with an 8-second interval. In one of the early studies, it was found that with distances between the bulbs of 20, 40, and 80 centimeters, the average perception of the interval was 6.5, 7.15, and 8.5 seconds respectively, although it was actually 8 seconds. This is called the kappa effect. It has been demonstrated many times and consists in the fact that the distance between events strongly influences the perception of the time interval. Again, as if the brain, at a fundamental level, links the concepts of space and time. After all, how do you represent chronology? Arrange the years 2021, 2022, and 2023 in order in your mind. The brain does this as if you were arranging three objects in space. It operates exclusively in spatial categories. It's even hard to imagine how one could do it otherwise, except by mentally living through those 3 years. And I bet you arrange them from left to right. If not, you're in the minority. Chronology in our brain almost always looks like a horizontal arrow pointing from left to right, and it seems natural. But why exactly like that? After all, the scale can be imagined any way you like. Since we use space to denote time, why not from right to left? Or from bottom to top? Isn't that more obvious? More like moving forward in time? No, people most often imagine it from left to right. There are many attempts to explain why the brain uses this particular spatial timeline. Buonamano says that perhaps it's due to the structure of our brain. For example, in an experiment where participants had to compare the duration of notes with a standard and determine which were shorter and which longer, an interesting pattern emerged. The efficiency of the solution depended on the button layout. People were faster and more accurate if for the short interval they used the index finger of their left hand, and for the long one, the index finger of their right hand, not the other way around. In other words, for a human, it is more natural to respond to a short signal with the left hand and to a long one with the right hand. Buonamano writes that it's as if in the neural circuits, the mental timeline is directed from left to right. Additional confirmations of the existence of a mental timeline were found in the laboratory of cognitive psychologist Lara Boroditsky. People who have suffered a stroke affecting the right parietal lobe of the cerebral cortex often insufficiently perceive objects located to their left, so-called left-sided spatial neglect. For example, such patients do not take food from the left side of the plate or even do not wash the left side of their face. Boroditsky and her colleagues proved that patients with left-sided spatial neglect have difficulty placing information about the past and future on the mental timeline. This leads to an inability to recall the temporal context of events. And finally, have you noticed that when talking about time, we constantly use adjectives and adverbs related to space? Looking ahead, looking back, winter is coming, a short life, a long time, and so on. Metaphors from the realm of space are often used to describe time, and very rarely the other way around, except for phrases like, "I live half an hour away." This phenomenon is found in all languages of the world. Buonamano writes, in general, we do not yet fully understand how the neurons of the hippocampus or other brain regions measure, reproduce, and store information about the magnitude of spatial and temporal parameters. But based on philological, psychophysical, and neurophysiological data, we can conclude that in our neural circuits, space and time are intertwined. You might object, time cannot be a spatial coordinate because it is very different from spatial dimensions. For example, when we move, we see the geometry of space change. Approaching objects, they seem larger, moving away, smaller. Nothing like that happens with movement in time. But that's not entirely true. At the moment of any movement, something unexpected happens. Objects begin to compress along your path of travel. For example, if you have good eyesight, you may have repeatedly noticed that when driving at 60 kilometers per hour, a car 5 meters long standing in front of you on the roadside, from your point of view, becomes shorter by about 8 femtometers and closer to you. If the 100-meter rocket Saturn V, on which the Americans flew to the moon, could reach a speed of 299,992,457 meters per second, 1 meter per second less than the speed of light, from the perspective of the astronauts on the rocket, the diameter of the moon would shrink from 3,474 kilometers to 284 meters in the direction of the rocket's motion. The name of this phenomenon is Lorentz length contraction. Extreme manifestations of special relativity are very far from our everyday experience. At the Massachusetts Institute of Technology in 2012, they even developed a 3D game showing how the world would be perceived in first person if the speed of light were equal to the speed of walking. The game takes into account almost all effects of special relativity. The slower you move in time, changing your position on the time axis, the more the geometry of space and objects in it changes. Yes, some effects are optical, but length and space contraction is real and observable. Even in this respect, time has observable spatial properties. Now that we've discussed the concept of time from the perspective of personal perception and physics, let's combine these two views. But that is exactly what's impossible, and therein lies one of the primary enigmas of existence. Of all the obstacles on the path to a deep understanding of life, no problem is as terrible as the problem of time. How to explain time without explaining life? How to explain life without explaining time? Uncovering the deep and hidden connection between time and life is a matter for the future. According to John Wheeler, life in general and humans in particular can move along spatial axes in both directions: forward, backward, left, right, up, down. Movement along the time axis always occurs in only one direction. People know this from their conscious experience. We can regulate the speed of movement in time, but not the direction. For us, time always moves forward and never backward. The fundamental laws of physics say nothing about why it seems to us that time moves forward. Newton's and Einstein's equations, Maxwell's equations, and the quantum Schrödinger equation do not depend on whether events develop in forward or reverse order. They contain no specific present moment of time. Despite all these compelling arguments that we live in a block universe, we have to admit, the laws of physics cannot explain the most obvious human observation. The present moment is different from all other moments, and time passes by itself. Einstein obviously adhered to the concept of the block universe, but he, apparently, was also troubled by this discrepancy between sensations and the modern understanding of the laws of physics. Philosopher Dolph Carnap wrote about a conversation with Einstein. Once he said that the problem of the now seriously worried him. The experience of the now means something special for man, something essentially different from the past and the future. But this difference does not and cannot occur within physics. That this experience cannot be grasped by science seemed to him a matter of painful but inevitable resignation. Roger Penrose, after describing the thought experiment with Andromeda, makes an important remark about the discrepancy between the subjective perception of time and the concepts of modern physics. According to the special theory of relativity, there is no such thing as now. The best approximation to it is the observer's space of simultaneous events in spacetime. An analogy comes to mind. The universe with all its events is a vinyl record, and our consciousness is the player's needle. But this analogy is absurd because consciousness is part of the universe, not something outside it. The impossibility of reconciling the idea of the block universe with the feeling of the flow of time is such a deep problem that many physicists and philosophers believe the only way to solve it is to recognize the sensation of the flow of time as an illusion. In my opinion, the biggest problem lies in the glaring discrepancy between physical time and subjective psychological time. The obvious sensation of the movement or flow of time, perhaps acquired through the back door of thinking, is the deepest mystery. Is it related to quantum processes in the brain? Does it reflect an objective property of time? Or is the flow of time exclusively a mental construct, an illusion or error of consciousness? According to theoretical physicist Paul Davies, this is one of the most fundamental problems in cosmology and understanding the nature of time. So the sensation of the flow of time is indeed a mental construct, at least because we perceive the surrounding world from inside our heads as a mental construct. As we said at the beginning, this applies to vision as well as to sounds and smells. They are illusions in the sense that they do not exist in the external world by themselves, but they have adaptive meaning because they correlate with real physical phenomena. The wavelength of electromagnetic radiation, a specific set of sound waves, or the chemical structure of molecules. That is, in the objective world, there is no blue color. Blue is an illusion caused by electromagnetic radiation with a wavelength of 470 nanometers. In the objective world, there are no unpleasant smells, but there are, for example, sulfur molecules that the brain interprets as the smell of rotten products. I repeat, Any such illusion has adaptive meaning because it strictly correlates with something that really exists. But then where did the sensation of time come from? Which, as we see, literally has no physical equivalent. This is not just an illusion in a figurative sense. It is an illusion in the most direct sense. In the block universe, our sensation of the flow of time is more comparable to the visions of a schizophrenic. It exists only inside us and does not exist in the objective world. Modern philosopher Craig Callender writes, "The equations of physics do not explain which events are happening right now. They are like a map that has no circle with the words 'you are here.' They have no present moment of time, and consequently, no flow of time." Resolving this mystery, uniting human perception with the laws of nature, is an extremely difficult task at the intersection of physics, neuroscience, psychology, and philosophy. Science is not yet able to comprehend the fundamental property of time that the human mind perceives as naturally as lungs absorb air. Or the human mind artificially attributes to time some property of its own making, not manifested in the laws of physics. If you ask me about this during working hours, I'll lean toward the second version. But in the evening, when critical thought slides into the routine of everyday life, it's hard not to agree with the first. Brian Greene, a theoretical physicist and one of the most famous string theorists, reminds us that the structure of the universe has left an imprint on the construction of the human brain. The brain really operates with spatio-temporal categories, as we saw from the analogy with the theory of relativity. Buonamano suggests considering the reverse option. Are we inclined towards one or another interpretation of the laws of physics because the brain interprets time in a certain way? That is, the laws of physics and the human brain are not independent of each other. Not only is what happens in the brain based on the laws of physics, but our interpretation of these laws is connected to the functioning of the brain. In other words, is the way our spatially oriented brain is structured related to the fact that, looking at the equations, we see a block universe in them. How impartial is the brain in its interpretations? Otherwise, a situation arises where humans themselves do not fit into the physical picture of the world they have created. It is important to understand, the laws of physics do not directly lead to an unambiguous conclusion that we live in a four-dimensional block universe. The idea of the block is certainly the most satisfactory interpretation, an attempt to directly explain what the equations of special and general relativity say. It is a generally accepted interpretation, but still only an interpretation. In physics, the struggle to create a complete theory capable of explaining the nature of time continues, and there is no unified opinion yet. Among scientists who adhere to the concept of the block universe, there are attempts to explain the sensation of the flow of time. For example, David Deutsch in The Fabric of Reality writes, "Objectively, there is no present. We do not feel that time flows. We feel the difference between our present sensations and memories of past sensations." Brian Greene adds, "Every moment in space-time is like a frame of a film, and each such moment for you is the present moment. You experience your sensations precisely in it, and this creates the impression of the flow of time. Each separate moment of time is rich in thoughts and memories, which enhances the feeling of constant movement of time. But in my opinion, this is more like an attempt to avoid answering than an answer. The struggle of various ideas will one day help us better understand the nature of time, or perhaps it will turn out to be even more unexplored and strange than it seems today." Thank you all very much for watching.